Organic Chemistry, Chem 212, Exam 3 Material, Part 1. Alkene Stability. They have found that cis-alkenes are less stable than trans-alkenes. This is through a comparison of the heat given off during a hydrogenation. The less stable isomer is higher in energy and gives off more heat. In comparing the heat given off when a carbon-carbon double bond is converted to a carbon-carbon single bond, the more stable alkene gives off less heat. Trans-butene generates 5 kilojoules less heat than cis-butene. Our graphic here is showing the cis and the trans, and the fact that the cis is a little bit higher energy than the trans was. Alkene stability. Alkenes become more stable with increasing substitution. This illustration here shows us the tetra substituted with 4 R groups around the alkene is much more stable, and this shows us most stable to least stable. Here's the tri-substituted, the di-substituted, and here we have the trans, and if you keep in mind on the previous slide, we determined that the cis is less stable than the trans, and then very close to that stability would be the di-substituted with a terminal alkene, and the least stable, the monosubstituted. 2 factors that contribute to alkene stability: hyperconjugation and bond strengths. Let's look at those. Hyperconjugation, an interaction that results from the overlap of a vacant p orbital with a neighboring bond. The more substituents present, the more opportunities for hyperconjugation. This illustration shows us the overlap that happens between the anti-bonding p orbital and the bonding CH orbital. This helps it become more stable. Bond strengths. sp2 to sp3 is stronger than an sp3 to sp3 bond. In 2-butene, this is a more stable molecule because we have a carbon on the left-hand side is written here as an sp3 hybridized carbon bonded to an sp2 hybridized carbon. This bond is much stronger than when we look at 1-butene, and on the left-hand side is written here on this 1-butene we have an sp3 to sp3 bond. In the 2-butene, we have 2 sp3 to sp2 bonds, where in the 1-butene, we only have 1. On this slide, let's go ahead and predict which one is more stable and why. Go ahead and pause the video and make your predictions, and let's see how you did. For letter A, the first structure that's shown only has 1 R group. It's a monosubstituted, where on this one, the carbon on the right is di-substituted. This one is more stable because we have more substitution, we have a di-substitution, and we also have the sp2 to sp3 bonding. For letter B, we are looking at cis versus trans. The trans was more stable. The number of R groups on this double bond on this side would be 2, and on this side would be a third one for 3. On this one, the number of R groups would be 1 on one side and 1 on the other for 2 total. We have a tri-substituted versus a di-substituted. This one's more stable. Let's take a look at writing organic reactions. You might have already seen some of them written where it doesn't look like there's a reactant there, but there really is. The standard way we've seen a reaction is where we have our, in this case, 2 reactants on the left-hand side of the arrow, and then we have the solvent and other reaction conditions. Well, with organic reactions, a lot of times we like doing the shorthand way of doing this. We will write the reactant also with the arrow and still the conditions. There's no established convention when we look at writing organic reactions. In fact, a lot of time they're done in shorthand. It can be a formal kinetic expression, but they're not necessarily balanced. Reactants can be before or on an arrow. Solvent, temperature, and details are still with the arrow. Electrophilic addition of HX to alkenes. We're going to be looking at reactions where the halogen can be bromine, chlorine, or iodine. For unsubstituted alkenes, or for symmetrically substituted alkenes, the addition of HX across a double bond appears to proceed in an identical fashion as the addition of halogens across a double bond. The reaction is successful with HCl and HBr. This is an example of an unsubstituted alkene, and we have our HBr in ether, and what's going to happen is we're going to have H and Br add across the double bond. The Br is going to add to one side of the double bond, while the hydrogen is going to add to the other side of the double bond. This is an addition reaction where our double bond goes away, and we now have more atoms on there than we did before. Go ahead and complete the reaction. Pause the video, come back, and see how you did. Did you remember to write ether above the arrow? And what's going on in this reaction? Again, this is an example of a symmetrically substituted alkene. When we want to add HI across the double bond, it's not as straightforward. We actually need to put a few more things inside of our reaction here. So we don't actually put HI in there. We put potassium iodide with H3PO4. And this will allow us to have the iodine adding across the double bond. In this case, it'll go to this side, and then hydrogen will be on this side. Explaining why the iodine goes where it does, that comes in a couple of slides from now. For unsymmetrical alkenes, the addition of HX across the double bond occurs with regiochemistry. If something is regiospecific, that means that one product forms where two are possible. Looking at our starting material, the carbon on the left-hand side of our carbon-carbon double bond has its disubstitute. It has two R groups on it, while this is a terminal alkene and there's only hydrogens on this side. What we're going to see that happens is hydrogen is going to go ahead and add to this carbon here, while our chlorine is going to add to this carbon here. We see here that we have 100% where the hydrogen went to the carbon on the right-hand side is written, and the chlorine on the left. We don't get any of the product where chlorine would go on this side. Let's compare that to another starting material. This hydrogen here is most of the time going to go to this carbon right here, and this chloride is going to go here. We're going to get mostly this, but very little of this. So why is there a difference between the two? It has to do with what carbocation is formed when hydrogen adds to the alkene. Let's take a look. The orientation of electrophilic addition following Markovnikov's rule. In an unsymmetrical alkene, HX reagents can add in two different ways, but only one way may be preferred over the other. If one orientation predominates, the reaction is regiospecific. Markovnikov observed in the 19th century that in addition to the HX of an alkene, the H attaches to the carbon with the most H's on it, and X attaches to the other end, to the one with the most alkyl substitutions. Now, that's the pragmatic way of looking at Markovnikov's rule. H adds to the side with more H's. The true definition of Markovnikov's rule is written in red here. Markovnikov's rule: hydrogen will add to the side that will produce the more stable carbocation. So the pragmatic is what we're going to use when we're actually writing out reactions, but if you're asked to put the definition of Markovnikov's rule, it's the one we have here: hydrogen will add to the side that will produce the more stable carbocation. Carbocation structure and stability. Hydrogen adds to the double bond first. That's something we need to keep in mind during all of these reactions. Hydrogen adds first. It will add in such a way that leaves a more stable carbocation, ready for the halogen to add and complete the reaction. The more stable a carbocation is, the longer it will exist as a carbocation so the reaction can finish. Let's take a look at this picture. HBr, we have our carbon-carbon double bond. What's going to happen is hydrogen is going to be slightly positively charged and bromine is going to be negatively charged. Hydrogen is going to be attracted to the electrons in the pi orbital. Hydrogen is then going to add to the carbon on the side with more hydrogens. Now this graphic doesn't show you more hydrogens here, but keep that in mind. This would be the side with more hydrogens. What that will do is it'll form a carbocation. This is a vacant p orbital, and this is known as a carbocation. The number of R groups on our carbocation will determine if it's a tertiary carbocation, secondary, primary, or methyl. And we're going to see, as we did before, The more substituents on there, the more highly substituted it is, the more stable it is. Carbocation structure and stability. Tertiary carbocations are the most stable, then secondary, primary, and then methyl. This illustration shows us in the order of increasing stability, whereas up here I show you the more stable. So let's take a look. Methyl is the least stable. That means it doesn't want to form as a carbocation as a methyl for very long. In fact, most likely, instead of the hydrogen adding on there, it'll be expelled and this carbocation will never be formed. Whereas on a tertiary carbocation, that's very stable, and the carbocation is going to hang around long enough for the halogen to realize it's there, and the halogen can complete the reaction. If we're comparing two carbocations next to each other, for example, a tertiary and a secondary here, these two, this is why we had that situation on the earlier slide that said mostly this and a little of this. That's because they were next to each other, and they're both pretty stable. In fact, tertiary is the most stable. But the first reaction that we saw that had 100% and 0%, that's when we were comparing a tertiary carbocation to a primary. Primary could never form. The energy of carbocations, looking at that with Markovnikov's rule, the more stable carbocation forms faster. Tertiary carbocations and associated transition states are more stable than primary. Here we have a tertiary carbocation, and this is our first transition state. Here's our intermediate. Here's our second transition state where the chlorine's able to come in and finish the reaction, or it could have been the other halogen, versus a primary carbocation. The energy is much, much higher. It's less likely we're going to have that much energy in the reaction. And look how high the energy is for the halogen to even come in. So if we're comparing a tertiary to a primary, the primary is never going to happen. The tertiary is going to happen much quicker, and the reaction is going to finish before the primary transition state can even form. Taking a look at our starting reactants, this carbon here has 2 R groups. This has none. Hydrogen is going to go to the side with more hydrogens. This hydrogen is going to add to this carbon that has 2 hydrogens directly attached. This carbon has no hydrogens directly attached. We can't count his neighbor's hydrogen. It's this carbon only. How many hydrogens does it have? It has none. Hydrogen goes to the side with more hydrogens, and that's going to form the more stable carbocation. In this case, it'll be a tertiary carbocation, and then chlorine can add to this carbon here. Let's take a look at this group here. We have this carbon here has 1 R group, while this carbon here has 2 R groups. This one's more highly substituted. It's going to form the more stable carbocation. That means hydrogen is going to go to this carbon here, while the halogen is going to go to this carbon here. Back to the mechanisms we were looking at. When we took a look, this hydrogen went to this carbon. Notice it has 1 hydrogen directly attached while this has none. That means when this hydrogen attaches, this will have 3 R groups. That would be a tertiary carbocation, and we're going to have mostly that. Now, every once in a while, because this carbon here has an R group on it, every once in a while the secondary carbocation will form where the hydrogen goes here, but it's not as likely to happen. In fact, you'll get very little of this other product. What you would do in the reaction is you would only list this product here because that's the one that is going to be predominant. You really don't get enough of this to even really talk about it. Let's take a look at the mechanisms that happen in both cases. In the first case here, it says mostly this. The pi electrons are going to attack the hydrogen. The pair of electrons that were holding the hydrogen and the halogen together are going to go just to the halogen. This forms a tertiary carbocation. We have 1, 2, 3 R groups. This is stable enough for the halogen to come in and finish the reaction. In this case down here, if the pi bonds attack the hydrogen, and again the pair of electrons go to the halogen, and the carbocation, this is where the hydrogen goes to this side, and the carbocation is formed on this side, this is a 1, 2 R groups, this is a secondary carbocation. It's not stable enough for this halogen to come in and finish the reaction. Most likely what will happen is this is not going to even form quick enough. The tertiary one's going to form quicker, and this reaction will be complete. The Hammond postulate, transition state structures. A transition state is the highest energy species in a reaction step. By definition, its structure is not stable enough to exist for one vibration. But the structure controls the rate of the reaction. So we need to guess about its properties in an informed way. We classify them in general ways and look for trends in reactivity. The conclusions are in the Hammond postulate. The Hammond postulate helps explain Markovnikov's rule by explaining the relationship between the reaction rate and the intermediate stability. So what is the Hammond postulate? The structure of a transition state resembles the structure of the nearest stable species. We've seen these energy diagrams before. Here we have a reactant. Transition state is the highest peak that it gets, and here's the product. In this case, the energy of our products are higher than the initial reactants. This would be an example of an endergonic reaction. Because the transition state is closer to the product, it resembles the product. In letter B, here's the reactant. The transition state isn't as high, and the product gives off more energy. In fact, it ends up being at a lower energy than the reactant was. Because the transition state is closer to the reactant, and the transition state resembles the reactant. When you have a reaction involving a carbocation, the carbocation is close to the transition, so the carbocation resembles the intermediate. A transition state should be similar to an intermediate that's close in energy. When we have a carbocation formed, the transition state looks like the intermediate. Evidence of mechanism electrophilic addition rearrangement of carbocations. We're going to be looking at what's known as a methyl shift. And what's going to happen is our molecule itself is going to rearrange. And we've seen evidence of this, and they wanted to know why would this happen. Well, the reason why something is going to shift is because it's going to become more stable. In fact, the reason why anything ever happens in chemistry is for it to become more stable. So let's take a closer look at this. The most likely evidence of these two-step mechanisms are that some products are formed from rearrangement. These products cannot be formed if it was a single step. There is evidence of a hydride shift in some reactions and a methyl shift in others. A hydride shift would be a hydrogen shifting. A methyl shift is an entire CH3 group moving. Let's take a look at this graphic. We have 3,3-dimethyl-1-butene. They have this methyl group over here in blue so we can watch it shift. Now remember, all three of these methyl groups are identical to each other because we have free rotation around this carbon-carbon single bond. So they're just picking on one right now. It could have been any of the three. So let's just pick on this one for right now. The pi electrons on our carbon-carbon double bond are going to attack this hydrogen. The pair of electrons that were bonding the hydrogen and chlorine together are going to go to the chloride, forming an ion. Once this hydrogen, now let's see, it's going to go to this side first because this side has more hydrogens, and let's see, we have the pink one here, so that's what it shows. So we have a carbocation formed here. This is a secondary carbocation. Well, what can happen, and this is what they saw some evidence of, is one of these methyls can shift over to this carbon here. When it shifts to this carbon here, this carbon now has its 4 bonds, but the one that it came from now becomes a carbocation. So why would it do it? Well, we now have a tertiary carbocation that is more stable. And this one is going to be around longer, because remember when we talk about stability, that means it can hang out a little bit longer. And the chloride can come in and substitute in this spot here. Now there will be some times where the chloride on the secondary carbocation will come in, and we will see this product also. So we have seen evidence that this is a two-step reaction, that a carbocation is formed. And it's due to this methyl shift here that we can say that a carbocation is formed as our intermediate.